The next algorithm we're going to build is selection sort. This works kind of like the way humans sort. Find the biggest thing and put it at the end. Then find the next biggest thing and put it next to the end, and so on.
When we build selection sort, we think of the array as being divided into two parts, the sorted part and the unsorted part. The unsorted part is at the lower indices of the array, and the sorted part is at the upper indices. When we start, the unsorted part is the whole array. Our strategy is to find the biggest value in the unsorted part and swap it with the thing in the last position of the unsorted part. That makes the sorted part bigger by one space and the unsorted part smaller by one space. Keep doing that until the unsorted part is empty. Let's look at an example. When we start, the whole array is unsorted. The biggest thing in the unsorted part is 52. So we swap that with the 5 that is the last thing in the unsorted part. Now the sorted part has one thing in it. We just keep doing that. The biggest thing in the unsorted part is 50, so we swap it with itself because it's the last thing in the unsorted part.
Yes, we swap it with itself. If this was going to happen a lot, we could add a check so that we wouldn't bother. But that isn't really worth the effort right now. Swapping it with itself doesn't hurt anything.
Now our sorted part has two entries. The biggest thing in the unsorted part is 42, so we swap that with the 5 that is the last thing in the unsorted part. That makes our sorted part have 3 entries. Now the biggest thing in the unsorted part is 16, so we swap it with itself because it is the last thing in the unsorted part. Now we have only 2 things left in the unsorted part. The 5 is the biggest thing in that part, so we swap it with the -3. Now our unsorted part has only one entry. One thing cannot be unsorted, so the whole array is sorted and we're finished. So the strategy for finding the biggest thing in the unsorted portion of the array is to start saying, well, the first thing is the biggest thing I've seen so far. So essentially we put our finger on that one. And then we walk through the array, and at each position we compare that position to the biggest thing we've seen so far. If it's bigger, now that's the biggest thing we've seen so far, and we keep going comparing to that. So you see in this animation, it has the max at the bottom, and it's keeping track of the biggest thing it has seen so far in that time through the loop. And then when it gets to the end of the unsorted part of the array, it swaps the biggest thing it's seen so far with the last thing in the unsorted part. And that's how the sorted part gets bigger by 1. Then we go back and we do it again, walking through the unsorted part, finding the biggest thing we've seen so far, and in the end, swapping that with the last thing.
Okay, I see how it works, but I have no idea how to build that.
Fair enough. If we try to think about the whole thing at once, it's overwhelming. Let's look at the pieces of the algorithm to figure out how to build it. The good news is that we already have a method to swap 2 positions of the array, so step 2 is done. We can write a method that walks through the unsorted part of the array, finding the biggest thing, so that takes care of the first 2 steps. The last 2 steps essentially describe a loop that tracks where the sorted part of the array starts. It starts at the end of the array and subtracts 1 until it gets to 1. That's when the unsorted part of the array is so small that it has to be sorted. That is a count-controlled loop, so it'll be a for loop. You can use that for loop, the method that finds the max of the unsorted part, and swap to build selection sort.
This is a good example of creating a method so you can build parts separately. Finding the biggest thing in the unsorted part of the array has a few border cases. Since we're building it as a method, we can write JUnit tests for just that part of the algorithm and be really sure that it works before we put it into selection sort. Doing it separately will make it easier to debug than if we had just tried to build selection sort all at once.
Let's do the runtime analysis of selection sort. The operation that happens most often is the comparison when we're looking for the max value in the unsorted portion of the array. The "is this bigger than the biggest thing I've seen so far" comparison. For each position we're sorting, we will have to go through the entire unsorted portion of the array. So, when we look for the biggest thing the first time, it will require n-1 comparisons. The next time will require n-2 comparisons, and so on, until the last time, which only requires 1 comparison. We can simplify that sum by rearranging it and grouping the values from both ends. n-1 plus 1 is n-2 plus 2 is n-3 plus 3 is n, and we can do that all the way until we hit the middle of the sum. If we assume there are an even number of things in the sum, the last grouping will group n over 2 plus 1 with n over 2 minus 1, which is also n. This gives us n over 2 minus 1 terms, each of which is n. So our runtime is n over 2 minus 1 times n. Since we drop lower order terms and constants, that is big O of n squared.
It's important to notice one thing here. We did the runtime analysis before we wrote the code. Being able to measure and compare strategies of algorithms without having to build them first is really important. That lets us weigh alternatives without having to build them. So we can think about and compare lots of choices while we're designing our system, and only build the one that we think will work the best.
So, both bubble sort and selection sort have runtimes that are big O of n squared. If we were only optimizing on runtime, we'd have to build both and do an empirical study to see which is faster. However, there are other characteristics that we weigh in these comparisons. For software, the biggest cost a company building software has is paying for their software engineers. So a solution that is easier to build will be cheaper to build. Once a system has been built, we enter a phase called maintenance. In that phase, we are adding new functionality and fixing bugs in the software. A less complex solution is less likely to have bugs and will be easier to add new stuff to. That will reduce our cost of the maintenance phase. We call that maintainability. We also might be able to save costs if we can purchase a solution instead of developing it ourselves. So when runtime is the same, we might use these other characteristics to pick a solution. In the runtime analysis we've done so far, we could just think about the operation that happens most because all of the operations take about the same amount of time. However, if the data is stored on disk instead of in memory, accessing the data takes much more time than anything else. In that case, we'd count the number of swaps the algorithms do. Bubble sort might make a swap for each comparison it does, so its number of swaps would be big O of n squared, the same as we found before. Selection sort will only do one swap for each element, so its number of swaps is big O of n. So, if our data was stored on a disk, selection sort would run much faster than bubble sort.